Hello, everyone. My name is Isaac. I'm from Brazil, and I'm the second year of my PhD project at the Université Laval in Quebec. So today I'm going to present some partial results of my project, mainly concerning new constraints on the PTT metamorphic evolution of the Pontiac group in the Superior Province. My project is supervised by Professor Carl Guilherme, and is co-supervised by Professors George Bedouin and Crystal Laflame. Also, we work in collaboration with other professors, researchers, and PhD students for the Université Laval, and for other institutions as well. Before I talk about the Pontiac group metamorphism, I would like to briefly introduce the importance of a work and its link with the orogenic gold mineralization, which comprise a major part of our project. So it's well known that many orogenic gold deposits worldwide share many features in common, but the source of fluids have been a long-standing issue and yet are not well understood. Many works have reported different sources, including a meteoric water source, a magmatic fluid source, and a metamorphic fluid source. But in the past few years, the metamorphic fluid source has gained a large approval. In such a case, the fluids are produced during prograde dehydration reactions, where the mobility of gold is related to the devolatilization of large volumes of metasedimentary and metabasic rocks. Even considering different fluid sources, these deposits have formed over more than 3 billion years of Earth's history during periods of major crustal growth associated with supercontinent formation. However, the New Archean was a critical period extremely favorable for the orogenic gold mineralization, being responsible for a high percentage of the world's gold resource. While the main global episode of orogenic gold mineralization is well defined, there are several ambiguities on the Meso to Near Archean tectonics. Despite the Earth underwent important geological and geochemical transitions, the cause and links to the geodynamic regimes remains poorly understood, and there is no agreement on previous work on how we should interpret this period. If we should consider a plate tectonic regime, a transition regime, or a stand-lead tectonics regime. So the question is, how we can better investigate the geodynamic setting and the fluid sources in orogenic gold deposits? That's when quantitative metamorphic studies become available too. Investigations on the PTT metamorphic history have the potential to unravel the geodynamic settings. As observed here in this picture, the shape of the PT path and the time can reflect a particular geodynamic context. So with a better comprehension of the geodynamic setting, we are then able to understand the energy source, the driving force responsible to mobilize the mineralizing fluids at regional scale. And during the prograde metamorphism, these fluids would be generated by dehydration reactions, extracting not only water and CO2, but also ligands such as chloride and hydrogen sulfides, which are responsible for gold mobilization. There is no better natural laboratory than the Pontiac in the Abitibi subprovince to apply this approach. Major orogenic gold deposits in the Abitibi are associated with Destor Porcupine and the Cadillac Lake deformation zones, which makes the Abitibi one of the economically most important metamorphic terrains in the world. But in such a case, what favored the major gold endowment in these two deformation zones? If you compare with the other crustal scale shear zones, we cannot observe a large distribution of gold deposits. So some works have indicated that the metamorphic fluids mobilize gold. So the Abitibi may have a source of fluids nearby. If that's the case, were the golden buried fluids derived from the Pontiac? As a matter of fact, P.T. Carney collaborates identify the Pontiac metasedimentary rocks as a potential source for the major gold endowment in the Abitibi subprovince. However, the relationship between the Pontiac prograde metamorphism in the volume and time of the fluid release remains unclear. The Pontiac subprovince is mainly formed by thick turbiditic sequence with concordant komatitic and basaltic flows, recording a Barrovian-type metamorphism in a metamorphic age of 2657 million years based on lutation Hafnium Granite dating. There is an important plutonism represented by sanuctoid monzonite suites and S-type granites. Antoine Godet will talk more about it in his talk on Monday. And so far, there are 4 tectonic models proposed for the Neo-Archean evolution of the Pontiac subprovince. An exotic terrain model, where the Pontiac would represent exotic Arctic terrain collided to the Abitibi, and a cratonary prism model, where the Pontiac is interpreted as a cratonary prism formed close to the Abitibi arc in a subduction setting, and a reflective microcontinent model, where the mantle overturn events favored the opening of a stational basin, followed by a fast reaccretion subcretion of microcontinent blocks. More recently, the Pontiac was reinterpreted by RIAM and collaborates 2021 as a plume-related rift basin in the old Abitibi arc, developed between periods of short-lived subduction. So each one of these models has predictions in terms of metamorphic evolution expressed by PTT paths with a certain shape along a certain metamorphic field gradient. So what we're going to do is test these tectonic models by quantifying the metamorphic conditions of the Pontiac metasedimentary rocks. And once you have a better understanding of the geodynamic setting, we will determine the volume of metamorphic fluids released during prograde dehydration reactions. So in the past 30 years, there are 2 main works in our study area, which provide insights on the structural geology, the map of isogrades, and geochronological data from the metasediments. Here in the map represented in blue, as you can see. However, both works present a conflicting point of view on the structural geology. Kamihenneborg, 1993, recognized 2 naps with abrupt change in structural style, while the upper nap, close to the Abitibi subprovince, shows evidence of 2 folding phases. The lower nap in the south part of the area has no folding evidence. On the other hand, Gazin, 1996, proposed that the same fold patterns observed in the north part could be recognized in the whole metasedimentary sequence. Although these 2 works provide important geological insights in the study area, there is still a lack of quantitative metamorphic studies. And so far, we have accomplished 2 fieldwork seasons, the compilation of previous published structural data, the description of 110 outcrops and 125 sections. We have acquired whole rock data, micro-XRF compositional maps, Garnet trace element maps, and also we have performed electromicroprobe analysis, phasing equilibrium modeling, UPB monazite dating, and lutation Hafnium Garnet dating. Here, usually the outcrops for the Pontiac group form a series of weathers and discontinued exposures, but you still could find some good exposures. You can see some field furrows. Outcrop for the Pontiac composed by metapilites and metawacks, showing a bedding parallel to a schistosity, an alternate bedding of metapilites and metawacks. And locally, you could observe some centimetric starolite porphyroblasts in the metapilitic rocks. 5 metamorphic zones were defined with an increase of grade from north to south, starting for the biotite zone, where the rocks are formed by plagioclase, quartz, biotite, chlorite. The garnet zone rocks, where you can see prekinematic garnet porphyroblasts. The starolite zone, represented here by synkinematic staurolite and pretosynkinematic garnet porphyroblasts. We could see the kyanite zone with synkinematic and kyanite and staurolite and prekinematic garnet porphyroblasts. And the sillimanite zone, this is quite different for we observe in the other metamorphic zones. We could recognize two metamorphic mineral assemblies. The first one is composed by sillimanite, cordierite, staurolite, and melt. And the other mineral assemblage is mainly composed by quartz, plagioclase, and eumenite, observing the core of post-kinematic garnets. We have selected representative samples for all the metamorphic zones, but the biotite zone, to perform the phase equilibrium modeling. So here we have the different steps we took to retrieve the peak PT conditions for the metamorphic rocks. So first we use the whole rock geochemistry data, and then we choose the appropriate compositional system we want to model these rocks. From that, we are able to calculate the topology of the PT phase diagrams. Also, we carefully describe the thin sections, looking for textural relationship between the minerals and microstructures. And from that, we calculated the model proportions and the isoplates by using the macro-XRF compositional maps and the mineral chemistry data. After we finish calculating the PT diagram topology, the first thing to do is check if you can reproduce the equilibrium mineral assemblage observed here in thin sections. If so, we can then calculate the model proportions of the main phases and also calculate the isoplates by using grossular contents in garnet and anorthite contents in plagioclase, which gave us peak PT conditions of 6.2, 6.5 kilobars and around 550 degrees. Also, we were unable to calculate the Phi number concentrations from garnet and biotite, which may suggest that the isoplates were reset during cooling stages. So to prove this hypothesis, we calculated other PT phase diagram using structural water, where we're able to cross the Phi number isoplates from garnet and biotite, which gave us a Phi MEG reequilibration temperature around 500 degrees. This approach was applied for all the PT phase diagrams we calculated for the other metamorphic zones. So considering the Pontiac a typical Barodian sequence, we would expect a typical metamorphic field gradient starting for the biotite, passing through garnet, staurolite, and so on. But what we observe in reality is after calculating several peak PT points for the garnets, for all the metamorphic zones, we can see that the garnet zone rocks follows a different metamorphic field gradient than the staurolite zone and kyanite zone rocks, which may suggest different geological process in the Pontiac, different metamorphic events in the Pontiac. So we have obtained Lutetium Hafnium garnet ages for all the metamorphic zones, which is consistent with previously published ages from staurolite zone rocks in the south of Malartic and Val-d'Or. Here we can see some lutetium distribution maps for all the metamorphic zones, where you can observe oscillatory zoning and a well-preserved growth zoning with lutetium concentrated in the core of most of the garnets here, meaning that internal diffusion hasn't disturbed the system. So based on these observations, we interpreted this garnet ages as the time of prograde metamorphism and crustal thickening. We also performed some UPB monazite dating only for the kyanite and the sillimanite zone rocks, but because of the lack of monazite grains in the we couldn't analyze monazite grains in the garnet and staurolite zones due to the lack of these grains. For the kyanite zone, monazite yields age around 26-56 million years, which is similar what we have obtained for Lutetium hafnium garnet ages. But for the Siles-Malta zone rocks, the Monazite elds are older age of 67 million years, which represents a time span of 10 million years when we compare with the prograde metamorphic age. So with all partial results, we can draw two main conclusions for the Pontiac group metasedimentary rocks. First one, that Pontiac recorded early low pressure, high temperature metamorphism based on the presence of a cordierite, sillimanite, staurolite melt, observing this, the sillimanite zone rocks, and constrained by UPB monazite age at 67 million years, and a prograde medium pressure, medium temperature metamorphic event based on the mineral assemblies observing the most of the all metamorphic zones, and a phase equilibrium modeling with Lutetium hafnium garnet age in UPB monazite ages around 57 million years. So the next steps of our project include confront our new PT data with the existing tectonic models, so we can then unravel the Newarkian geological evolution of the Pontiac subprovince. Also, we intend to constrain the PT conditions, the time in the volume of oil-bearing fluids generated by the volatilization process, so we can then provide unprecedented sites at crustal scale metamorphic fluid generation. I would like to thank you for your time and attention, and if you have any questions, I'll be more than glad to answer. Thank you very much.
Sorry, Ross, I had one if nobody else does.
Yeah, please go ahead.
Yeah, very nice study. Maybe I missed it. Did you? It would be interesting to look at the neodymium isotopes in monazites in these rocks too, which might then give you a good constraint in terms of what the sources of fluids are that are moving around in the system, and that can be fairly easily done these days. Likewise, titanite and other minerals. Are you intending doing that?
No, we didn't plan to do it, but if it is, in case if it is easy to obtain this data, it would be great for us. Well, but I don't have too much knowledge about it.
Relatively easier. Speaking as someone who did his PhD in the 90s, when things like that were impossible, it's easier these days. Yeah, maybe easy was the wrong word, but yeah. Well, if you're in, I mean, you could either probably do that at Laurentian or I mean, we do it on a routine basis too. So, but I think it would be an interesting thing to do one way or the other.
Yeah. Thank you. I would like to think about this and talk with my supervisor to see if we still have able time to do it.
Yeah.
Thank you.
Isaac, this is Bruno Lafrance speaking. Just a general question. Have you been able because you were talking about naps and been able to recognize major shear zone thrust fault within the Pontiac?
So it's a good question. What our field observations are in good agreement with the Camihan and Berg observed in the 90s there, but we couldn't see the thrust fault zone there that separated the two naps. We couldn't recognize, but the same fold partners, we only observed in the north part, and in the south part, we didn't see it. So, but we didn't see a large thrust fault zone there.
Yeah, because one of the result, if you want, of Adrian Ram's study is that these ultramafic bodies within the Pontiac that were thought to be imbricated within the Pontiac along thrust fault are actually autochthonous to the Pontiac.
Yeah,
so I'm just wondering if I know it's difficult sometimes in sediment, but is there some place where we could put a major fault within the Pontiac?
Yeah, I couldn't see, but from previous work in the area, they say that the thrust fault would be separating the garnet zone rocks from the staurolite zone rocks. We know that there's some shear zones there, but unfortunately we couldn't see. We're looking for this evidence of thrust faults there, but we couldn't find any, unfortunately.
Okay, Thank you.
All right.
Thank you very
Thank you
much.
very much, Isaac. It was an
Thank you.
excellent presentation.